so long. So we start with the common emitter amplifier. First, I will write the various expressions that we have already developed in our previous discussions for the common emitter amplifier. The input resistance Ri was just R pi. The output resistance R0 was the small R0. Then the voltage gain V0 by Vs, which we expressed as the products of two gains V0 by Vb and Vb by Vs. VB was the voltage at the base, and V0 by VB was minus GM R0 in parallel with RA, and that multiplied by RI plus RS. And that was the voltage gain. The current gain was I0 by II, and that was minus theta. So these are the expressions for the common emitter amplifier that we already have developed or derived in our previous discussion, drawing the small signal equivalent circuit. So now we want to derive these parameters for the same circuit without drawing the small signal equivalent circuit. So just looking at the circuit and inspecting, right, the various parameters. Now RI, what is the RI? RI is the resistance looking into the base, between the base and the ground. So emitter is grounded, so that is between base and emitter. So that is our RI basically. And if you look between the base and emitter, the resistance that we have is known as the R pi. So RI is nothing but R pi. So here we write that, let's change this one. So from this inspection of the circuit, we write that Ri is R pi. So that's the same with what we got, right, by drawing the small signal equivalent circuit. So without a drawing the small signal equivalent circuit, just by visual inspection of the circuit, we are looking into the base, and between the base and emitter, since emitter is grounded, so the resistance between base and ground is R pi, Ri is R pi. So that's how we deduce the input resistance. Now, what's the output resistance? Right? So if you look into the output terminal, output resistance is the resistance that is between the collector and the ground. Again, emitter is grounded, and we know that between the emitter and collector and emitter, we have the output resistance that is known as the small R0. So that is what we have between the collector and the emitter, small R0. So I'm looking into the collector from the output side. So our obvious conclusion is that the output resistance will be small R0. So we write that our output resistance R0 is small R0. So that's pretty straightforward. By circuit inspection, we can easily determine these parameters. Now, voltage gain, how to determine the voltage gain, right? So voltage gain, again, it has two components. One is V0 by VB and VB by VS. So let's first write that VB is V0 by VS, and we express as the product of these two, VB by VS. Now, what is VB by V0 by VB? So V0 by VB, first we start with the expression V0. Right? We can write I0 RL, that is also okay, but instead of writing I0 RL, more, a faster approach will be to use this current, which we call the IC, right? The collector current, IC. and that current is passing through. You see that R naught is a small R naught here between collector and ground, and also we have the load RL between collector and ground. So basically these two resistances are in parallel, the small R naught and the load resistance, these two are in parallel. So we have this IC passing through this parallel combination, and we can write, since IC in opposite direction of, right, this in going upward, so we have minus sign here for V naught, and okay, so we have a minus sign, and that will be minus IC, and the parallel combination of R naught and RL. Now IC we know is given as GMVB, so that is from our knowledge of the pi model. In the pi model, if you remember, the current source is given as GMVB. So that is actually IC. Right? VB is the voltage between the base and emitter here, and IC is given as this. So we replace this one for IC, we get minus GMVB, and we have R naught parallel combination of RL. And VBE is nothing but VB. So we can also show that in the circuit, less confusion. If we convert this, so this is basically our VBE, right? Between base and emitter. But emitter is grounded, so VB and VB is same. What we write here that our VB is same as VB. So V naught we can then express as minus GM VB R naught parallel combination of RL, and from there you can express this V naught by VB as minus GM R naught parallel combination of RL. So that's how we determine the first part here, V naught by VB, and second part VB by VS, just as we have already shown in many cases for the single state transistor amplifier. Ri is our input resistance from this point to this point, so this part is Ri and then Rs. So and voltage VB is the voltage at this point. So applying the voltage division rule, this we just write as Ri divided by Ri plus Rs. So that is pretty straightforward, and then it's put into this expression for AV, the two gain expressions. First is minus GM R naught in parallel with RL, and then we have the second part Ri plus Rs. So check this one, this expression and the expression that we have here. So these two are basically same, right? So that is how we can derive the gain for the amplifier circuit. You just analyze on the circuit as it is. You don't need to draw the small signal equivalent circuit. And the current gain is much easier with just the output current I naught divided by the input current, right? Now output current here is not directly IC, so you need to probably apply the current division rule in this case. And if you apply current division rule, then you can write that I naught is, since IC in opposite direction, upward, so IC divided by R naught divided by R naught plus RL. Now, as we have said in previous discussion that this R naught usually much larger than RL, right? So if you ignore this RL here, it becomes 1, and this you can approximate to IC. So I naught will be almost equal to IC. So then this I naught is minus IC. So we have minus IC, and I is the base current basically. So it's IB, and IC by IB is beta. So we write minus beta, and that is the same what we got with from the small signal equivalent circuit analysis. Guys, any question? Hello, guys.
No, sir. No, sir.
Okay. So next we'll check the common collector. Here collector is grounded. We take the output from the emitter. That is our output resistance. And from here, we have the input resistance. So first I write the expressions for the what we got from our small signal analysis. Starting with the input resistance. Input resistance was R5 plus beta plus 1 RL. Remember, common collector has a high input resistance and the low output resistance. Output resistance was small RE plus RS divided by beta plus 1. And then we had the voltage gain. Again, was expressed like this, similar to what we wrote for the common emitter amplifiers. So that is V0 by VB times VB by VS. V0 by VB was written like this, RL, then RL plus small RE, and VB by VS, we have same expression as common emitter, RI plus RS. And then we had the current gain, AI, which is I0 by II, and that was beta plus 1. So these were the expressions for the different parameters for the amplifier. Now we'll see how we can derive these different parameters, parameter expressions, using our shortcut method. Right? So starting with the input resistance Ri. Now what is Ri? We're looking from the base, right? We're looking from the base side. So looking from the base side into the base. So when looking into the base, so first what you have here, between base and emitter you have R pi. Looking from the base side you have resistance R pi. Now that will be added with the load resistance RL. But load resistance RL is in the emitter side, it's not on the base side. And we are looking from the base side. So when you're looking from the base side, what you will see? Hello guys, we'll have R pi, and in addition to that, we'll have RL, but will it be just RL or what?
So it will be multiplied by factor beta plus 1.
Right. So here the resistance reflection rule will be applicable here because it is in the emitter side and looking from the base side, so that will get multiplied by beta plus 1. We have a beta plus 1 times R. And so let's see that this resistance what we have got here is the same as what we got from our small signal analysis. So that is our Ri input resistance, and now we try to find the output resistance R naught. So in this case, looking from the output side and looking into the emitter, right? Now looking into the emitter, so we have to now trace this path. So first from emitter to base. Now when you're looking from the emitter, what you see a small R, right? Looking from the base, you see R pi. Looking from the emitter, you see RE. So first you will have small RE. So first you will have this small RE, and that will be added to, we have this RS. Now what we will see from the emitter side, because RS in the base side.
So again resistance reflection rule.
Yeah, and in this case, what we will have?
So this time divided by beta plus 1.
Right. So looking from the emitter side, the resistance from the base will be divided by the factor beta plus 1. So we'll have RS divided by beta plus 1. Right? So we get low output resistance because RE is small and RS also gets divided by beta plus 1. Makes the output resistance small for the common collector amplifier. So we have determined the input-output resistance, which is exactly the same what we got from our small signal analysis. Now we try to determine the voltage gain and the current gain. So voltage gain is again expressed as the product of these two factors, V0 by VB and VB by VS. So first we start with this expression V0 by VB. Now VB is the voltage at the base, so that we can, okay, so we show this voltage VB that is at the base, is voltage VB. And V0 is the voltage at the emitter, right? So what we can write V0 by VB. Can you figure it out? No one knows.
Sir,
Is
V
very
not
easy.
or I not RL uh, or IERL.
Then what is IE?
Uh,
It's
I
complicated. When you have this V naught by VB like this, right, the ratio of two voltages, you apply voltage division rule, right? Can I apply voltage division rule here? Say V naught is the voltage at the emitter. We are on the emitter side, right? V naught on the emitter side. So, and VB is the base voltage, right? So looking from the emitter side, so if you think of the T model, because in the T model, it is from the emitter side. So in the T, if you think about the T model, we have something like this. That is our base point, right? And that is our emitter point. We have the small RE, and then you have the RL, and here is the V naught, and that is the base point, that is the VB. And this goes to the collector, right? You have the current source. Anyway, so that's not needed here. So if you look at the circuit here, right, this is the series combination of RE and RL. V naught is the voltage across RL, and VB is the total voltage. So that is how the circuit will look like, because we are on the emitter side. V naught is on the emitter side, RE is also from the looking from the emitter side. Then what we can write for this ratio? Yes.
Sir, RL divided by RE plus R.
Yeah. So we can write RL divided by the total resistance, RL plus R. With the same what we have here, you see, the first part. And obviously second part is just VB by VS RI divided by RI plus RS. That is same for all the amplifiers, right? From the input side, I look from the input side. What happened to this? Okay. So now if you substitute here, V naught by VB is RL, and you have RL plus RE, and that times VB by VS is RI plus RS. So that is what we have here, right? The total voltage gain expression, and finally the current gain, which is quite straightforward. I naught by II. I naught is our same as the emitter current. It's connected on the emitter side, and the current that is flowing here. Current that is flowing is our emitter current. Right? So I naught is IE, the emitter current, and II is our base current. And IE by IB is nothing but beta plus 1. So that is what we have, beta plus 1. Any question, guys? No question. Okay. Okay, now we'll see the common base amplifier. What we get from the common, how we analyze the common base amplifier circuit. So here base is grounded. We take the output from the collector. And we apply the input at the emitter. Maybe I can show it like this better that way. That is our input current here, and we have the output current. Resistance looking from here is the output resistance. Resistance looking from here is our input resistance. Now, what will be the input resistance here? R, I. Now you try to solve this one.
Sir, RE.
Right, so Ri will be just a small Re. You see that basically we are looking into the emitter. So look into the emitter, this is the emitter point. So basically Ri is the resistance between the emitter point and the ground, right? The emitter and ground, and we have the base is the ground, right? At the same point. So if you look into the emitter, what you see between emitter and ground is the small r. So Ri will be small Re. As you know, the common base has a very small, very low input resistance, lowest, right, among the three configurations. Re is very small. So that is our input resistance. And what's the output resistance? R naught, what is the output resistance?
Sir, R naught, and then a complicated term, I think.
Then?
So then a complicated term. There will be
Complicated term. How complicated? So if you have a circuit like this, you have a resistance in the emitter, right? You have a resistance in the emitter and from the collector side. So for this circuit, we didn't show the derivation because it's not important. It will take one whole class, not worth it. So that's the circuit analysis. So if you are looking from the collector and you have a resistance in the emitter, then the resistance, the output resistance is given as with this expression R naught that is multiplied by a factor, complicated factor, as you have rightly said. And that complicated factor, it has just two terms, not that complicated. First one is just R, first one is just one, right? And second part is Gn times, there are two resistances. One is this Rs, one is this Rs, and that in parallel with, the other is the resistance here, the R pi between the base and emitter. R is in parallel with R pi. So that's not very difficult to remember. We have R naught resistance between collector and emitter looking from the output side. We first see this resistance that gets multiplied because of R. So this R naught gets modified, right, by this modifier gets multiplied by this factor, that is 1 plus Gm R is in parallel with R pi. Whatever resistance is here, that in parallel with R pi. So that is our output resistance, and we get a very high output resistance because R naught is already high, and that getting multiplied by this factor makes it very high output resistance. So we have determined also the output resistance. Now we try to determine the voltage gain, AV. So in this case, we just directly write the voltage gain as, there is a more straightforward, V naught by Vs. So what is V naught? What we can write for V naught?
So minus IC.
Yeah, first we write I naught and I, and I naught is minus IC, minus ICRF. Okay. IC is the current that is going into the collector, so that is our IC. So I naught IC in opposite direction. So this is our V naught. And what is Vs? What is Vs? You see that the circuit here we can draw like this at the input side. We have Vs, and then we have Rs, and then we have Ri. Right? There is looking from this point onward is Ri, and the current that is flowing II. So this current times the total resistance. Current is II, and we have Rs plus Ri. So that's pretty straightforward, nothing complicated. That's the Ohm's law, right? Current times the resistance with the voltage. And what is the II?
So minus IE, emitter current.
Right. You see the current here, the emitter current is flowing in this direction. So that's the opposite of the current II. So II in this case basically is minus IE. Right? So here we write that that is minus IE times Rs plus Ri. What we can write for Ri?
RE.
Small Re, right? So we can replace for small Re. So that is our Vs and that is our V naught. So now you substitute in this expression. So you have minus V naught is minus ICRL, and that you have minus IE Rs plus RE. Minus and minus will cancel out, it will become plus, and you have IC by IE, and that times RL, and you have Rs plus small r. And what is IC by IE?
Sir, alpha.
Right, so that is alpha RL RS plus R. Right. Alpha is approximately 1, so we approximate this to 1 and write the gain as ratio of these two resistances. As we said in our previous discussion, for the gain of this common base amplifier, RL is the resistance that is connected to the collector, and RS and RE is together, that is the total resistance in the emitter. So usually this gain expression we can express as the collector, the total resistance in the collector divided by our emitter, total resistance in the emitter. So that's easy way to remember the gain expression for the common base amplifier, the resistance in the collector divided by resistance in the emitter. So that is the gain expression for common base. And if you remember that, you can straight away write down the gain for the common base. Right? You don't need to go through all these derivation steps. Clear, guys? Any question? So some of these expressions you need to remember, right? If you are doing analysis of a much more bigger circuit, right, where you have many transistors. So deriving all these steps is not very practical in those situations. So that is our the gain, voltage gain for the common base, and then finally the current gain, which is actually pretty straightforward. This I naught by I naught is minus IC, and I is minus IE. Minus and minus cancels out. IC by I is alpha. So that is almost equal to 1. As you say, compare the common base has almost a unity current gain, right? Unlike the common collector, which has a unity voltage gain, common base has a unity current. That's the current. Any question, guys?
No, sir.
So did you get the idea how to analyze the circuits directly on the circuit itself without drawing the small signal equivalent circuits? Right? Okay, so now our main discussion on multi-stage amplifier circuits. Okay, where I'm coming this. Okay, multi-stage amplifier, we can have two different configurations. We have already probably mentioned that. One is cascade configuration. The other is the cascade configuration. So first we'll discuss this on the cascade configuration, then we'll see the cascade. Now, how the multi-stage amplifier improves the amplifier performance. Of course, if you want to improve the gain, then then probably you can add two common emitter amplifier, right, in series. This one has gain A1, this one has gain A2, right? Then overall gain will be V0 by Vi is the product of these two, A1 and A2. So this is how you can improve the gain, right? Otherwise, if you are using a single stage amplifier, like one is just a common emitter amplifier, right? And gain is A. So what happens, the single stage common emitter amplifier, it has a low input resistance. So that is, we said that that is a drawback for the common emitter amplifier. So in order to overcome that, what we do, we add a voltage buffer. In this case, common collector works as a voltage buffer, so we can add a voltage buffer which has a high RI, and this has a high, it has a low. So that will overcome this limitation, and it can improve the overall gain, right, of the amplifier. So first we see this example of common collector, common emitter, and so we have these two transistors. First one is Q1, which is connected in common collector configuration. Since collector is grounded, input is applied to the base, and we are taking the output from the emitter of Q1, and that goes into the base of Q2, and Q2 is connected in common emitter configuration. So the emitter is grounded, input applied to the base, and we're taking output from the collector of Q2. Okay. So, and this is our input resistance from, seen by the source, and that will be our output resistance seen by the load at this point. This is what we call So this is our common collector, common emitter, cascade amplifier. So there's a two-stage amplifier. We have a two-stage amplifier. We can have more number of stages. You can have two common emitter amplifier in series so that you can have further higher gain. Now we would like to determine the different circuit parameters here. So let's start with the input resistance and output. Those are pretty straightforward. So what will the input resistance Ri?
So 2 R pi.
Those two are pi.
I think so, sir.
Resistance looking from here between base and emitter. That is R pi 1 for the transistor 1. And resistance looking from this point. What is the resistance here?
So this is also R pi, but there will be a factor beta plus 1.
That will be R pi 2, no? From 1 to this one. So the input resistance Ri, we are looking from the input side, base of Q1. So if you look here, so Ri will be R pi 1, and then we have plus. Now we are in the emitter side of Q1 and base side of Q2, and we have resistance here R pi 2, right? So what we will basically see from this point?
So won't be there a factor beta plus 1 into R pi 2 or something like this?
Right. So since we are looking from the base of Q1 and R pi 2 is in the emitter side of Q1, so it will get multiplied by beta plus 1 times R pi 2. Right? So look at this expression that without the common collector, just the common emitter had the resistance of R pi. Now when you add this common collector, the input resistance increases by almost this factor beta plus 1, R pi gets multiplied by beta plus 1. There's a significant increase in the input resistance. Right? If beta is 100 and R pi is 1K, then it becomes 100K. Right? If R pi is 2, then it becomes 200K. Right? There's a significant increase in the input resistance. And that will minimize the loss to a great extent. So that is our input resistance. And output resistance, what is the output resistance?
So the output resistance from the common base configuration.
Common base. Why do you find the common base here? This is the common emitter. No?
Yes, sir. But in this part, it is the the resistance between collector and base.
Why collector and base?
Oh, sorry, sir. Sorry. The collector and emitter. Then it will be R naught.
Right. So if you look between the collector and emitter, what we have? The collector and emitter, you have the small R naught, right? The small R naught collector, and that is the ground. So the R naught will be the small R naught, and we can add the subscript R naught too for the second transistor. So that's the remains same as the output resistance of common emitter. Common emitter output resistance is R naught. So that remains same because the output side, we didn't change the output side of this amplifier. We only modified the input side. We added a common collector at the input side. So input resistance is modified, but output resistance remains same. Now we'll try to find the voltage gain. What is voltage gain? So before, sorry, this will be VS. So when we assign some voltages at different nodes of the circuit, so this is base of Q2. So let's call it VB2, base voltage of Q2. This is the base of Q1. So let's call it VB1. So now the output rate, sorry, the voltage gain. V0 by Vs, we can split it up like this. First V0 by VB2, and then VB2 by VB1, and then finally VB1 by Vs. Right? So that is how we can express this voltage gain as the product of the three gains, right? Since we have a two-stage amplifier. Now we need to determine individually these different gain factors. Let's start with the first one, V0 by VB2. What will be this gain expression, V0 by VB2? So in this case, now this is the situation where you need the help of your this power of memorization, right? So if you can store this information in your memory, then you can just retrieve it and just put it. This. What is the gain expression?
So the gain expression from collector common emitter
Right.
minus GM R1 by R1 into RI divided by RI plus RS.
V0 by VB2.
Yes, sir. Minus GM into, then it will be R naught parallel. Yes, R naught parallel RL. Then then the input resistance divided by input resistance plus the source
Why
resistance.
input resistance? Why input resistance? That is the overall gain, no?
Yes,
We
sir.
are talking about V0 by VB2. If I go back.
Oh, sorry, sir. It was the overall gain. Yes.
So we are talking about V0 by VB2 from the base to collector, right? V0 by VB. And
Yes, sir.
V0 by VB is just this, minus GM, R
Yes,
naught and RL.
yes,
Then
sir.
if you are trying to find the overall gain, then you have this VB by VS, and that is RL, RI plus R. So we're not there yet. We are just at the output side. And so just V0 by VB2, that is minus GM2, that times the small R naught, that is R naught 2 times RA. So you just remember the gain expression for the common emitter and just put it here, right? Otherwise, you will need to go through all the derivation steps and you will run out of time, not be able to finish the exam, right? A lot of problems. So that's the gain for this part, and now the second part, VB2 by VB1. So what will be that? VB2 by VB1. Yes, we have already done that now. This is for gain for common collector. Let's take a look at the gain for the common collector. This is our common collector, and we're trying to determine this gain V0 by VB. Right? There it was VB2, this was VB2, and this is VB1. So the same as here, V0 by VB1. From base to emitter. For common collector, output is at the emitter, input is base. So from base to emitter, the gain. What do you see here? So that we apply the voltage division rule from our this T model. Right? So you have to have this in your in your imagination, the T model of this the transistor. Here we have we are in the emitter side, we have RL, and here we have RE. So in that case, in our this current example, here we have, instead of RL, we have what we have here.
Sir, R by 2.
Right, exactly, R by 2, and here.
Sir, instead of RE. Sir, R by 1.
R by 1, are you sure? Okay, let's go back. So we are here, right? So we have here R by 2, that's in the emitter side of the Q1. And we're looking, if you look into the emitter, what do you see? Looking into the emitter of Q1?
RE.
Right, the small RE, RE1. Now if you think about the T model here, on the base point, you can draw like this. You have here R by 2, and then here you have RE1. Okay? And that is your base point, which is the voltage VB1, and that is your emitter point, and voltage is VB2, right? So that's how the circuit will be if you draw the T model of the circuit, and you can see the applying the voltage division. I mean, you don't need to draw this, right? It's very straightforward. See, the resistance here is R by 2, and you're looking into the emitter here, resistance is RE1. So these two are in series, and voltage are VB2, voltage is VB1, base point. Just apply the voltage division rule. It's pretty straightforward, right? Okay, so applying the voltage division rule, we write this R by 2 that given by total resistance R by 2 plus R1. Is that clear? Any question else?
Sir, there was a slight
Okay.
confusion. Sir, in terms of determining VB2, the resistance for VB2, we are looking from base to emitter. But while
Yeah.
determining VB1, we are looking from emitter to base. So this is a, so why this inverse relation, sir?
How do you want to look?
Sir, same direction.
Same direction.
Uh,
From where? If you are here,
yes,
right? VB2 is the voltage at this point.
yes, sir.
There is the point we have voltage VB2.
Okay,
And we are in the emitter of Q1. We are trying to determine the voltage gain for Q1, which is connected in common collector configuration. And what is connected here, right? At the emitter, that is acting as a load. So this one is like the load for it is like acting like a load for Q1. The input resistance this one is like the load resistance for Q1. So if you want to draw the, I mean, if you want to replace this part, whole of the Q2, just you want to show the Q1, the equivalent circuit for Q1. Q1 doesn't know what is connected, right? You have connected Q2, but Q1 doesn't know what is connected with this, if it is a transistor or resistor, whatever. So if we replace this whole Q1 by R by 2A and equivalent resistance, so the current voltage, everything remains same, nothing will change. Do you get that point?
yes, sir.
So that is what we have in our also that circuit we have shown you. The see that RL, right? Load resistance for the Q1, and that is the input resistance for whatever is connected here. This load is whatever is connected at the output of at the emitter of Q1. That is like the load resistance. It can be a resistance, it can be another circuits, right? You don't know that. So that we can replace by RL and it will be same. Okay? The input resistance of the same circuit. Now this part we look into the emitter because we are the emitter side, right? So whatever will be connected to RL, that has to be in the emitter side. You cannot look from here. So that is in the base side. And base side current is II. Now the same current has to flow. If you want to apply the voltage division rule, same current has to flow through both the series combination. You cannot have a R pi and RL here because R pi, if you put R pi, then it will be current will be IB. But RL current is IE, right? So they cannot be in series or you cannot apply voltage division rule in that case. We have to have same current flowing, right? So since RL is current, the emitter current is flowing, so you have to look into the emitter and see what is the resistance between emitter and base. So there is small RE and same current is flowing. So the voltage at the base point is voltage. You know, you can apply the voltage division. Is that clear? And that is what we got from the small signal analysis as well. Right? When we did the small signal analysis, that is the expression, and that verifies that what we are doing here, we are doing the right thing. We are not doing the wrong thing. Right? Our approach is correct, 100%. There is no doubt, because we are getting this exactly same expression what we did using our small signal analysis. Any question?
No, sir.
So that you have to little bit think over in your head, right? To get your conception clear. so that you don't get confused, right? Because we will frequently encounter these situations while analyzing these circuits. So VB2 by VB1 is given by this. Now only part remaining is VB1 by VS. VB1 by VS, and that is pretty straightforward. The same for all amplifiers. They have said that is input resistance Ri plus Rs. So the voltage gain here will be V0 by VB2, which is minus GM, not 2 in parallel with RL, and times R by 2, R by 2 plus small Re1, and that times we have Ri plus Rs. So that is our total gain expression. Any question? Okay, now let's see the current gain, and then we'll finish this. It's a small part. Let's try to determine the current gain. So to determine the current gain, like voltage gain, we assign the different voltages. Now for the current gain, we need to assign the currents at the different branches at different points. So first start with this current here. There is the collector current for Q2, so we denote as IC2. Then current that is flowing here, there is the base current for Q2, so we denote as IB2. And then the current here at the emitter for Q1, that is our IE1. And then current II is same as IB, right? We call it IB1. This is how we assign the different currents. Okay. So current gain is our output current divided by input current. Now this we can express like this. First I0 divided by IC2. Then we have IC2 by IB2. Then we can write IB2 divided by IE1. Then we can write IE1 by II. Right? So that's pretty straightforward. Now we see what are these different currents. First I0 we it's just the IC2 but flowing in the opposite direction. So I0 is basically minus IC2 and divided by IC2. And IC2 we keep same as this IC2 divided by IB2. IB2 and IE1, right? So IB2 basically same as IE1, so we can replace IB2 by IE1. And here we have IE1 and II. II is nothing but our base current, IB1. So now it's pretty simple. Now you see that IC2 will cancel out. Here IE1 and IE1 will cancel out. And so the overall current gain with a minus sign. IC2 by IB2. What is IC2 by IB2?
Sir, beta.
Right. So it's a beta. Beta 2 can write beta 2 is what is second transistor. Then IE1 by IB1, what is that?
So beta plus 1.
Right. And you can write beta 1 plus. So we get a high current gain, right? Or you can say very high current gain, because the product of its almost beta square, right? If beta is 100, then it will be 10,000, very high current gain. And voltage gain, is there any change in voltage gain? So this is the gain for the common emitter. This part we get for the common collector. And this is basically almost equal to 1, because RE, the small RE is much smaller than R5. Okay? If you ignore this part, it will be almost equal to 1. So basically it reduces to this part and this part. So basically these two are, we have same as common emitter. But what is the difference here? The common emitter we have this remains same, so doesn't change. But here RI, right? The RI is much higher, right? For common emitter, RI is only R pi, but now in this case, this R pi is much higher than R pi, right? Almost, if beta is 100, almost 100 times higher. So what happens? This will be much closer to 1, right? So this whole expression, because R is we expect not that high, but even if it is high, then even then there will be significant improvement in this factor. It will be much higher, and the loss will be much minimized. So loss in the source resistance is much higher because they have very high input resistance. So by adding the common collector, the overall gain will be improved, right? Overall gain will be, you get a higher gain by minimizing the loss. Any question, guys? Okay, so we discussed the one and the multi-stage amplifier, the two-stage common collector and common emitter. We will see further modifications and also different multi-stage amplifier circuit examples in our next class. Okay, so what we do now? Then we show.